Okay, so today we get to move beyond those little baby features, okay, onto some real features. So this is sort of image processing content where we're going to talk about, not just machine learning, but image processing as well, which some of you may have dabbled a little bit in. Probably most of you are interested in that. It's really cool. Actually, we're looking at proposing our master's degree. It's under review by the dean right now, and if you're insanely optimistic, it could start next fall, but I don't think that's going to happen. But anyway, the reason I say that is one of the courses that I'm developing for the master's program is a machine vision course. So this and lots of other really cool stuff will be part of the machine vision course. So what I'm going to do first is start with a demonstration of some of the things that OpenCV can do, and then show the theory behind it, how it's actually calculated. Okay. And right now what we're going to be talking about first are edge features. How do you detect edges in an image? And you'll notice that in this problem we're trying to find these cones. And if you can find a cone-shaped edges, you can identify that in the image. So that's sort of the idea here. So I'm going to go ahead and run this code. It's going to produce a whole bunch of figures. Okay? And let's go back to the beginning. The beginning is we have this beautiful little toucan. Okay? I don't know why I picked a toucan, but I ripped this image off the web. So here we've got a toucan. The first thing I did is convert it to grayscale. Okay, you can, if you want, detect edges in all of your color layers. You could do, where are there red images? Where are there red edges? Where are there blue edges? Where are there green edges? Certainly that's possible, and it may be important for certain problems. What's more typical is you just convert to grayscale and look for a single edge in the image. So that's the first thing we do, is we get this nice grayscale image. Okay, and then I use what's called a canny edge filter. Okay, so that's this line 15 right here that creates edge, and this is just the result of what is returned by the canny function. And basically what it does is it takes your original grayscale image and it returns an image of the same size that's a binary edge image, where any pixel that is white is detected, quote unquote, as an edge, and anything that's black is not an edge. Okay, and we'll talk a little bit about how this works, and how it goes from the regular image to the binary image. But there are some parameters that you can change. You'll see that I'm passing a 50 and 100, and there's two threshold values. The most important one is the second one, the higher of the two. And basically, the higher you make that value, the fewer things will be detected as edges. Let me put this guy over here, and we'll mess around with that a little bit. Okay, if we change that to 200 here, you'll notice that there will be fewer edges. Okay, I changed that up to 500, there's even fewer. Change it up to 900, there's even fewer edges. Okay, and if we go and look at the original picture, okay, it's only detecting now the strongest edges, which are, basically the branch that he's sitting on, in some parts of it. See over here, this edge is not detected. It's sort of a fuzzier image. It's not quite as stark of an image as the right side of the toucan's body. Okay, and so that's a design parameter, and this is one of the things I'm talking about that had led me to be less enchanted with neural networks and some of these machine learning things, because all of the classic, if you want to call them, machine learning approaches, you have to develop features. And you have to develop really good ones. It's not like you just come up with some weak feature, weak classifier built on a weak feature. You're trying to find really good ones that work well. And then once you identify the good features, then you have a machine learning algorithm that learns the relationship between the features and what the labels should be. Okay? But you've put all of this intellectual capital into developing really good features and choosing the right parameters for these things. Okay? And so what we'll find is when we do the last project, when we do convolutional neural nets, it's kind of like AdaBoost in the way that it will pick what features it wants to use. But not only, you're not even giving it a list of features, it develops the features from scratch, which is really cool. Okay, so you might be changing this around depending on how and the lighting of this image is going to change whether a feature looks strong or whether it looks weak, and so there's a lot of things that are involved in getting tuning just the right values for these parameters. Okay, so that's the canny edge filter. Okay, and that finds edges in general, edges in any direction. Okay, then the next one I do is a Sobel filter. Okay, and a Sobel filter, this is in the X direction and this is in the Y direction. You can actually make the Sobel filter be in any direction. You're looking for edges in any direction, and basically that 1 and 0 are kind of like telling you what the direction is, the X component and the Y component of whatever direction you're looking for. So it's most common to use that as 1, 0 for things in the X direction and 0, 1 for things in the Y direction. And so then we have figures 4 and figures 5 that are the output of the Sobel filter. Now you'll notice one difference between this and the canny is that the result is not a binary image. It's not just 0 or 1. It actually gives you strengths, how strong of a vertical edge or how strong of a horizontal edge is it. Okay? So this is when I'm looking for, when I'm doing a Sobel X, which is looking for vertical lines. It's looking at changes in the X direction of pixels. And then this one is looking for changes in the Y direction in the strength of pixels. Okay, and so you can see anything that is near is kind of like a vertical line is if it's a strong edge and it's almost vertical, it will be very bright here. Okay, and so that can be interesting to find in different directions. If you're looking for edges, maybe you're trying to find a rectangle or something, you're trying to find different sides, and you'd be able to find vertical sides versus horizontal sides. Okay, yep.
Is it possible to overlay these two images one on top of the other to get like this is all of the edges period?
Right. So he's asking if you can overlay the two on top of each other to find, are there edges? And that's basically what canny does. We'll see. Canny is based off of both a Sobel X and a Sobel Y, and essentially it uses that to find the strength of the edge. Okay? And you can find its direction as well. If you look at it like a vector, and we'll get to that. Okay, so that's a good question because that's one of the contents that comes later. So that was a very observant question. All right, so how do you get these things? How do you work out these ideas of getting these edge detections? And it's based on a concept called convolutions. And what's really interesting is, if you're paying attention, what I said, our last project is going to be convolutional neural networks. Okay, and so this idea of convolutions is as old as image processing. It's basically when you hear of image filters. If you ever hear that term, that is a convolution. So sort of convolutions of filters are synonymous. And so the idea of a convolutional neural network is based off of this idea of a convolution. Okay? So let's say we have our image, and our image is, it's really annoying. I don't have the same image. Anyway, I don't have the same picture on my screen that you do. So this 5 by 5 matrix is your image. And in this case, it's it's a binary image. The pixels have either 0 or 1 values, just to make it simple. Okay? And what we're going to do is we're going to overlay, we're going to have this kernel. Ooh, there's a typo in the kernel. That should be a 1. Sorry about that. That should be, well, my whole kernel's messed up. Let me fix that. I really messed that up. That should match the times numbers in there. It should match them. 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, that's right. And I'll re-upload this so there's not any confusion.
Why is the bottom left 1?
Why is this a 1?
The bottom left of the kernel.
Here? Right there?
can't see your mouse.
Oh, you can't see the mouse, can you?
The bottom left of the kernel.
Why won't it let me
Is
show?
that 0 times 1, or is it
No.
you're changing it to a 1?
There we go. Okay, this one right here?
Yes.
Okay, so the kernel is independent of the image.
Okay.
Okay, so different quote-unquote filters are use different kernels. Okay, so you pick a kernel and then you apply that kernel to an image. So the kernel and the image are independent. Okay, and so the red numbers in here are the values of the kernel. Now the kernel happens to be a binary kernel and the image happens to be binary, again, just to be simple. So this one right here is this one. That 0 is that 0. This 1 is that 1. That 0 is that. That 1 is this. That 0 is that, and so on. Okay?
I think the notation just threw me off because it looked like 0 times 1.
And it is. It is going to be. This is going to be 1 times 1.
Okay.
And that is going to be 1 times 0, 1 times 1, 0 times 0, 1 times 1, etc. So you're going to make all those multiplications and you're going to add the results together. Okay? So you see here that you have one thing that's 1, another thing that's 1, another thing that's 1, and another thing that's 1. There's 4 things that give 1 and the rest give zeros. And that's why this kernel applied to that portion of the 5 by 5 image gives a value of 4. Okay? Now, if we let it go to the next, okay, now we shift the kernel over 1 pixel and apply it again. Okay, and so now it's, look at the kernel, watch the kernel up here, 1 0 1 0 1 0 1 0 1. Okay, so the kernel has stayed the same, it's just gotten shifted over 1 pixel, and again we're going to multiply the values in the kernel times the values in the image and then sum them all together. And here we have one thing that's 1, another thing that's 1, and another thing that's 1, so the value for that is 3. Okay? And then we keep going. Okay, we move the kernel over, we get another value, we move the kernel over. So it's sort of like the sliding window search. So we're sliding this kernel across the image to get all the values. Now, I don't know, I've had trouble, sometimes it doesn't. I copied a GIF file and made it into a movie file and it didn't do the last one. But it should shift that over and do the last one there and get you a value. Okay? And so basically you're doing a sliding window search. You can kind of think about it. You slide this kernel across the image and you're getting values. Essentially, how well does the image match the kernel, essentially? Kind of. That's one way to think about it. Okay? Now, generally what we're after is we're trying to get a value for every pixel in the image. But because the way we start this, let me go back to the beginning. The way we start it, if I'm going to put the kernel in the image, I'm going to get something where the kernel is centered at this pixel. Okay? And so that 4 is a 4 that it's associated with the center of the kernel. And kernels always have odd by odd so that there's a center pixel to them. So the value 4 is the value of this convolution evaluated at the center of the kernel. So you notice if I have a 3 by 3 kernel, all of the pixels on the outside edge of the image don't get values. Okay? And sometimes that doesn't matter, and sometimes it does matter depending on what you're doing. Okay? If it does matter and you want a value for the kernel at every position in the original image, you can do what's called zero padding. And with zero padding, this blue thing is your original image, and what you do is you make that image bigger by putting zeros around the outside edge. So all the dotted positions are an enlarged image where you put values of zeros there. Okay? And the amount that you would need to pad is going to depend on the size of the kernel. If you have a 3 by 3 kernel, you have to add zeros around the edges. If you have a 5 by 5 kernel, you need to add 2 rows and columns of zeros around the image to make it pad. And so now you can see when I have this 3 by 3, this is the gray thing is my 3 by 3 kernel, and it's now being applied where the center of the kernel is in the top left part of the image. And I'm going to get now a value for the kernel in the end. And so of course we can play this guy, and you can see it you can see that it will slide across, and now the results that I get are going to have a value for every point in the original image, so my resulting features are going to be the same size as the original image because of the zero padding. Okay? And that's how we're able in this, in showing you the results, that the size of the edge image is exactly the same size as the original. It's not 1 pixel smaller all the way around. Okay? So that zero padding is really helpful for us to be able to keep things the same size. Okay? Now, like I was saying, the kernel is something you decide independently of the image. And the kernel is going to depend on what are you trying to do. Okay? And there's all sorts of different kernels you can use to do different things. One of them is to find edges, and we'll talk about this right now. We'll also show you another kernel that's part of the canny edge filtering that will do a noise reduction. Okay? So to start off with, let's look at the Sobel kernels. Okay? So this guy here is for detecting vertical lines. Okay, so they call that GX because I'm looking for differences in the X direction, and it will find vertical lines. This one will find that one will find vertical lines. Right, and then this one will find horizontal lines. Okay, so these are 3 by 3 Sobel kernels. Okay, and essentially what it's doing is it's subtracting the values of the pixels on the left from the pixels on the right, where something in the middle is like the edge. And it's not so the pixels in the middle of this 3 by 3 don't count at all. Things on the right count positive, things on the left count negative. Okay? So you can imagine if you have the same pixel value on the left and the right, you'll get 0. Okay? So if there's no change in the horizontal direction, you get 0. If you have a big change in the horizontal direction, you get a big number. Especially if the pixel in the middle is a big change. Okay, so here is a way of visualizing this guy. So we have an image here. This thing is 5 by 5. Okay, and here it has actual pixel values between 0 and 80. Okay, and so they actually shaded the color. Apparently this is a green layer, so they shaded the color of the pixel depending on what the value is. Okay, so we have our kernel exposed in the top left here. There's no padding here, so we're going to end up with something that's smaller. Okay, and so we're going to check. You know, here's -1, -2, 0. So here we're doing this guy, actually the flipped version of this guy. Okay, and so I'm comparing. Essentially, I'm comparing this pixel to this pixel, and these pixels in the middle don't count. They have zeros. So I'm checking, is that different than that? Well, that minus that is 0. They're the same, so it doesn't contribute. Okay? That minus that, that's 75. That contributes. That's an edge. Okay? 80 minus 75, well, it contributes a little bit. There's a difference of 5, not a difference of 75. And not only, this guy is in the middle, that counts as 2. So not only is it 75, it's 2 times 75. So it's getting a value of 150 plus 1 times the difference of 5. That's where the 155 here comes from. Okay? Then we can move over. Let's see, so we move over. Come on, let's move over. So now we shift it over. Now I'm comparing 75 to 0. That's 70. That counts 75. 80 and 75, that's 5. That counts as 10. So that gives me 85. 80 minus 80, that's nothing. So there's an 85 in that pixel, etc. And then we keep scanning that guy across, and we end up now with and for some reason it's not doing the last part of the animation, but I'm getting a 3 by 3 result from my 5 by 5 because I didn't do any zero padding. Okay, so now you can see here, okay, this pixel here is the strongest edge. And so now you can see how I'm getting a result. This is the Sobel that gives me every pixel. How strong is it an edge in either the vertical or horizontal direction? And that's why it's not a binary image when we display it. Okay? So that's Sobel. Pretty straightforward. Yes?
So positives and negatives are determine the stronger edge, because is it not the displacement between the two, and it actually matters whether it's positive or negative?
Right. So you're right that what we're looking for is the change in the value, whether it's increasing or decreasing. Okay. So if this, for example, had this been 75 here and 0 there, I would have gotten negative 155 instead of 155. Now, for it to be an edge, it's the absolute value that matters. Okay? But the sign will tell you in which direction is it increasing. Okay? And so usually we're not interested in the sign, we're just interested in the magnitude.
So the bottom edge is the strongest edge.
So if it's positive, okay, if the Sobel value is positive with this kernel, which is the opposite of this kernel, by the way, okay, if I use this kernel and the value is positive, that means it's dark on the top and bright on the bottom.
Okay.
But again, usually we're not worried about which direction is the edge, but whether there is an edge. But you might be interested in an application. I want to know, where is it getting brighter, where is the edge going from light to dark down? That might be important for you, and you could use the sign here to be able to tell that. Okay. All right, so that's Sobel. Now, here's another kernel, this guy down here. Again, that 1 divided by 273 is actually a shorthand to say you take every value in there and you divide it by 273. Okay? And you're like, whoa, that's really weird. What the heck is this thing? This is some strange 5 by 5 kernel. Okay? And you'll notice the largest value is in the middle, and they get smaller the farther away you get from the middle. Okay? And this is based on a Gaussian probability distribution, okay, a bell curve. And this is the equation here for a bell curve centered at 0. Okay? I could have a shift in it if I didn't want it centered at 0, but in this case, we do want it centered at 0. Okay? And the value sigma is the standard deviation of this normal distribution. So any of you guys that have taken prob stat, you know all about what I'm talking about. The rest of you are like, I don't have no clue. Okay? But basically, it's a way of measuring how far you are from 0. Okay? And the sigma, like I said, it has to do with the standard deviation. And really the standard deviation just says whether this is going to be a skinny, tall curve, or whether it's going to be a short and fat curve. Okay? Now the shape of the curve is the same, it's just whether it's tall or skinny or short and fat. Okay? And you'll notice this weird sigma divided by sigma the square root of 2 pi. All that does is it makes sure that the area underneath this curve always sums to 1. And that's something you need for it to be a probability distribution. You want the integral from negative infinity to positive infinity to equal 1. Okay? So it's just a scaling factor to make sure that this thing always sums to 1. Okay? So that's the Gaussian distribution in 1 dimension, and in an image, obviously, we're talking about things in 2 dimensions. So a Gaussian in 2 dimensions, this is what the equation looks like for a Gaussian in 2 dimensions, where the standard deviation is the same in the x and the y directions. You could have different standard deviations, but here it's the same. Okay? So you can see, and this factor here makes sure that the volume underneath that surface sums to 1. Okay? And so this here is just a discrete version of the Gaussian 2D normal distribution. Okay? And this divided by 273 is what I need here to make sure that I sum all of them together and I get 1. Okay? Now, if we apply this thing to an image, this kernel to an image. Obviously, the pixel in the middle where I'm applying it is going to be the most important one. But it's not going to be all. It's not 100% of the result. Portions of it are going to be dependent on the pixels that are around it. And the farther away I get from the center, the smaller the contribution is to those pixels. Okay? Anyone want to guess? What does this do?
Reduces noise.
Yeah, well, I already gave that away. I told you. Okay? And this is Wikipedia has a really good article on this, and they show this is the images that I get on Wikipedia if you look at Gaussian convolution kernel or Gaussian noise reduction. And so the original image, it gets fuzzified with the higher standard deviation. If you have a very tall and skinny distribution, then only the pixel in the middle counts. And the ones near it, very little. The shorter and fatter, I'm taking more and more information from around in the neighborhood, and I'm getting it to be fuzzy, which is kind of interesting. How we lose detail. Obviously, we lose detail as when we apply it. But if there was noise, if there were either noise due to electronics, or if there were if there was a bunch of birds in the foreground, the birds, the effect that the birds would have on the color would be lessened. Okay? And so I bring this up just to show you another type of a kernel that does something different. And there's all sorts of kernels that do all sorts of crazy stuff. Okay? But the main reason I brought that up is because that's the first step in doing the canny edge detection, is that first they apply a Gaussian filter to reduce noise. So they do that automatically for you. And then they do the Sobel X and they do the Sobel Y. And then they calculate the overall gradient. And that's what somebody was talking about, okay? Of taking the two pieces and combining them to know, what is the total strength. Because that's in the end what canny is about. It's an edge, not what the direction of the edge is. Okay? So you can think about the GX and the GY as being normal components to an edge of a gradient. Okay, and this brings you back to, I don't know, was it Calc 3 when you do gradients of vectors? Anybody done Calc 3 yet? Is that when you do gradients of vectors? Yes. So in Calc 3 you'll talk about gradients of vectors, and that is how much, if you have a surface plot and you want to know in which direction does the value change the most. I mean, if you have a two-dimensional plot, there's only one direction. It can even increase going one way or increase going the other way. It's either positive or negative, like we were talking about, Tim. But if you have a surface, the direction of the most increase or most decrease of the function can point in any direction. And that's what the gradient will tell you, is in which direction is the value increasing the most and how much is it increasing. If I move a little bit in that direction, how much will the value increase? That's what the gradient gives you. And you think about it as a vector. How much does it change going one way? How much does it change the other way? And then whichever direction, when you add those two things together as vectors, that gives you the amount of the change going in the direction of the highest amount of change. And you can think about whatever angle that's pointing at. Okay? We'll talk a lot more about this gradients, because this is how we're going to train neural networks to optimize their parameters. We're going to head in the direction of decreasing the error as much as possible. Okay? So this gradient idea will pop back up. All right? So we'll calculate that gradient, and we're going to apply a threshold to the gradient. Okay? And so let's skip this first thing about thin lines. Let's talk about applying the threshold first. Okay? So we're going to have a gradient value, okay? And the stronger that value is, the stronger the edge is. And we're going to set a threshold. Boom! Anything above 100 is going to be considered an edge. Anything below 100 is not an edge. And then you can change that value as we did. We made it 900. When we made it 900, there weren't as many pixels that made it over that threshold. Okay? Now, there's also this lower threshold. Okay? And this builds sort of a no man's land. Anything that's above the top threshold is automatically an edge. Anything that's below the lower threshold is automatically not an edge. Anything in between is considered an edge only if it's touching an edge that is above the threshold. Okay? So that allows some things below the upper threshold to be considered edges as long as they're continuing something that's already strong. So it allows you to be able to follow lines. You know there's something strong, and you can follow that line wherever it leads until you get below that lower threshold, and then you say, hey, well, enough is enough. Okay? So then the most confusing piece of the canny edge detection is this idea of non-maximum suppression, which is really interesting. That this is going to come in again for us when we're doing some stuff later with the cone classifications. Okay, and basically what it's going to look at is, let's say you've got an image, and you have let's say this is the direction of the edge. Okay, and there's some points along here that have certain gradient values. Okay, and that edge is kind of thick because, you know, maybe there's multiple ones that are above the 100 threshold. Okay, and so then you get a quite thick, and you'd have this thick line as your edge, and it won't be a very nicely defined edge because it might be many pixels wide. So what they do is they look in the direction of the edge, and there's many pixels that are above the threshold, and they'll throw away all but the largest one. Let's say non-maximum, anything that's not maximum is suppressed. So whatever pixel has the largest value in that direction of the gradient is the one that's kept, and the others are thrown away. And that way you get nice thin edges rather than big thick lines. Okay, so that's the one of the other pieces that the edge detection does. And here's some documentation to the canny edge detection. You can go to that URL, and it describes basically what's on the slide. Okay. All right. So that's canny edge and Sobel edge detection. And now you're going to ask yourselves, okay, I've got this beautiful edge image. How do I use that to build features? Say I want to find, is there a toucan in this image? How do I use whether there's edges in there to know whether there's a toucan or not? So this is only the start. This is image pre-processing. This isn't even the feature. We took our original image and we changed it into a binary image that has less information but more relevant to what we're trying to find, and now we want to do something more. Now I found an amazing web page. It does a great job of describing this idea of the histogram of oriented gradients. There's the URL up there. It has a ton more information describing in more detail than what I'm going to cover today. Really good. Spot on. Okay? So they are taking this image of Usain Bolt, okay, and they want to get some information from his edge stuff here. Okay, so what they're going to do is first we need to decide how many cells to break this thing into. Okay, because we want to know if there's edges in particular places in the image. Okay, and so first we need to decide how big is a cell going to be in terms of pixels. And in this example, we're using 8 by 8 pixels to form a cell. So you can see each one of the green rectangles is one cell of 8 by 8 pixels. Okay, so what we're going to do is we're going to take each one of these, and take one cell at a time, and look at each cell, and we're going to put an edge filter over top of that to find a gradient. Okay, and so each pixel in here is going to get a gradient, and this here is the gradient magnitude. Okay, and then we're also going to find what is the angle, what is the gradient direction of that. Okay, so that's the G and the theta that I was showing you before. Okay, and the values in these two matrices are visualized here by drawing arrows, where the direction of the arrow is obviously the direction of the gradient, and the length of the arrow is how strong the gradient is. Okay, so you can see here there's basically no gradient. You don't see anything because there's no change in pixels there. It's all gray. Okay, here you can see there's a big change. That thing there versus that is a big change. But that value and that value is not very much, so there's quite a strong vertical gradient in the image here. Okay, so this is beautiful to be able to visualize these two matrices. Okay, so we got this cell, I've got all these gradients, and I'm going to turn them into a histogram. So basically I want to know for this particular cell, what is the dominant direction or directions of gradients in this cell? Okay, so what we're going to do is we're going to create a histogram out of this, okay? Where basically every pixel in this 8x8 matrix is going to get to vote on its suggestion on where the strongest direction is for gradients in this cell, okay? So for example, this pixel right here, he votes for 119 degrees. Okay, and he gets 76 votes because it was 76 strong. So the stronger the gradient is for a pixel, the more votes it gets. So this pixel right here, it's going to vote for 80 degrees, but it only gets 2 little bitty votes. It's kind of like the electoral system for, for electoral college. Okay, that's Rhode Island right there. Okay, they don't get much of a say because they don't have strong gradients. Okay, and you also notice that they take anything, they have only, the angles are only between 0 and 180 degrees. Basically, they take away the sign. They, if it's this way or that way, it's the same direction. We don't care which direction it's increasing. Okay, and so you build this histogram out of how many votes does each position get. Now you have to decide how many bins am I going to divide the histogram up into. Okay? The more bins I get, the higher resolution I get in my angle. Okay? But the more data I need to be able to get reasonable things to show up in there. Okay? So in this, we look at this histogram and you can see bins near 0 and bins near 180 have stronger values. So this lends you to believe that in this particular cell now, it's more vertical. The gradients are more vertical than anywhere else. Okay? All right. Now, here's another an odd thing that it does, is it does a thing called normalization. And it's an attempt to try to adjust for lighting and contrast variations so that we're really seeing that we're able to compare apples to apples. Because if in one part of the image it's very bright, and another part of the image it's not so bright, we won't be able to compare the histogram values very well. So what they do is they do what's called batch normalization. So we have to decide how big what we call a block is, and the blue square is the blue rectangle is square as a block. And in this particular case, we're using 2x2 cells to define a block. And what we do is for inside a block, we take all of the histogram values in there of the 4 cells. So there's 4 histogram values. If we have 9 bins, we're going to have 4 times 9 histogram values. And we're going to normalize them so that they sum to 1. Sound familiar? Just like the thing with the probability distribution. We're going to add all of them together and divide by the total amount to get new values that sum to 1. And then you can go ahead and add them together and you can show they do sum to 1. So we're going to normalize over a region so that we normalize things and so we can compare apples to apples. Okay? So here is a visualization of the results of that. So for each cell, okay, we have now all of the directions, and what these red lines are showing you is all of the directions that are getting the high votes. Well, the high vote, the length. Well, I'm not sure exactly how it's doing it, but it must be just that all of the directions that are strong are having lines in them. I guess that must be the way it is. So for example, this guy right here, okay, it almost looks like a circle. There's lines drawn in every direction. Okay, so all the directions have equal strength. Now they're all weak there because there's not very many gradients, but they all have equal strength. Okay, here you can see there's only lines that are diagonal, so that has a gradient in the diagonal. This is vertical stuff, that's horizontal stuff. Okay? And so now, if you were to take away that image, take away the image of Usain Bolt there, actually I have that on the next page. Okay? Here is the image, here is what's visualized actually using Scikit-learn. And this is a little different. If you compare this image basically it's showing which are the ones that are, which are the directions that are strong compared to the others, no matter whether they're actually high gradients or not. And what in Scikit image does, and you'll notice every direction has the same strength of red. Okay? Basically, what we do here is the strength of the direction is going to depend on how white it is. Okay? So here, all of the directions are the same. They're just so weak that they don't get any. You don't see them because they're black. So it's a little bit different in the way he visualizes it on that web page versus what you get out of Scikit image. Okay? So if you take this guy right here, this thing here, you can see there's like a person in the middle, kind of. I mean, if you were to be blind and not see the left-hand side, you can say, okay, there's something there. It has the shape that could be a person. Now you see, you're also getting here, this is the line. That's the white line on the road. So I'm seeing that white line as well as I'm seeing the person. So hopefully whatever machine learning algorithm you are going to work on is going to be able to tell the difference between them. Okay? So here's some code. This is the code that creates that image. Basically, we need to import Scikit learns image, and then there's a feature submodule, and I'm importing HOG, histogram of oriented gradients. And you'll notice I could have done just import Scikit image.feature, and then I would have to write Scikit image.feature.hog every time I wanted to do it. But here what I've done is I imported only HOG, and I've allowed me to call HOG just simply by HOG. Now, if I had just done from Scikit.feature import star, that would import all of the functions, and they might actually have names that are overlapping with things that you have in there. So this is a way that you can just pull in one of them and not have to type a bunch of stuff before the HOG. Okay? So I load in Usain Bolt's picture, I convert it to grayscale, and then I run the HOG on it. I say how many orientations in my I set up these parameters, which I'll talk more about the next slide, and visualize true. That will return this second value, the HOG image, which is what I've displayed here on the screen. It'll always give you the feature vector, but it'll only give you the HOG image if you do visualize true. Okay? So in this particular situation, okay, I have 9 orientations of the histogram. That's why there's the 9 here. Okay? Oops. I have 8 by 8 pixels per cell, and I have 2 by 2 cells per block. So this is how I get the same results that I had in that example. Okay. Now, what does feet return? It returns a giant vector of all of your histograms concatenated together. Okay, and in this case, it's 3,780 features. Okay, and you can work out exactly. You don't ever really worry how many there are exactly. I mean, if I had done 100 bins on my histogram, I would have gotten a disgusting amount of features. You don't want to make it too big, but you want it to be big enough. Okay, and essentially the way I can get that 3,780 is there's 8 pixel. The original image is 64 by 128. I divide by 8 by 8. That tells me how many cells there are. And then each cell has 9 histogram bins in it. And actually, each cell is in 2 normalizations. You see, as this thing shifts across, let's see. So this guy right there is in both of those 2. So every cell is in 2 normalizations, so it has 2 normalized histogram values. Except for all the pixels around the edge, they're only in 1. Okay? So that's where the -2 thing here comes into. Okay? So that's how you calculate how many features you're going to get out of this. So now I've got 3,780 features, and we're going to use all of them. All in all their full glory. We're going to use all these features to feed into our machine learning algorithm. Okay? So you can see, we're not just going to pick the best 100. We're going to use all of them because they're all important in order to see what's going on in this image. Okay? So you can tell why you still need computational power. All right. Now, those HOG features are built off of the grayscale. Okay? So if there's information it has to do with color, it will be lost. So if you're looking for the yellow cones, that's obvious. There's nothing else yellow in these pictures, so it's important not to throw away all the color information. So one way you could do this is with a color histogram. Okay, we did this in MTRE 2610. Okay, you build a color histogram, and you go ahead and you can take all the histogram values for the red, all for the green, all for the blue, and you can concatenate them together into one big long 1D array. Okay. And here I did a little example. I've built a matrix X with random Gaussian random values in them, and then I'd go ahead and you can use the histogram function in in Python, in NumPy, to get you them, and this will give you a bar graph of the histogram. Okay, and this is for a one layer. You'd have to do this for all 3 of the layers of your picture. Okay. And yeah, okay. Now, this is going to give you the color histogram overall for the entire image. Okay? There's no localization. It's not that there's yellow here in this part versus there's not yellow here in that part. Okay? Now, I solved this problem with just this color histogram stuff in the HOG. Okay? You could imagine it probably would be better, say, if you broke this thing into cells like you do the HOG, and you get a color histogram for all 3 colors in each one of the cells, and then you concatenate all of them together. Then you would have localized color histograms. That, yes, there's yellow in the middle of this image and not yellow on the outside edges. That would be even more powerful. You probably could get even better results than what I did if you were to get, break it into cells and get localized color histograms. That would probably be even more powerful. Okay? Now, the last thing I want to talk about are color spaces. I've got 2 minutes here. We already know 2 color spaces, grayscale and RGB. Okay, and we know as we combine RG and B together, we get white. Okay, and the intersection of red and green give you yellow, etc. Okay, there's another color space called the YMC, yellow, magenta, cyan, and this is a subtractive one. If you take yellow and take away magenta, you get red. And if you take away everything, you're left with black. Okay, so you could do it that way. Okay, so that's sort of, there's an argument over, well, what are the primary colors? Is yellow a primary color? Well, yes, if you talk about a subtractive color space. No, if you're talking about an additive one. Okay? Now, there's another one that can be quite useful besides RGB, and that's the HSV color space. It still uses 3 values, so it still has 3 layers, but it's not how much red, how much green, and how much blue there are. Okay? It's how much hue, how much saturation, and how much value is there. Okay? And the reason this is useful is because only one of the layers tells you what its color value is. Okay? So the hue is your color. That's sort of where am I around the outside perimeter of this thing. So light blue is a value of 0 and green is a value of the maximum, 255 or whatever. And you vary continuously along here. It's sort of like going along the rainbow. Okay? Then the saturation is saying essentially how washed out is the image. If I have a 0 value for saturation, it's all white. I can't distinguish between any colors because it's so washed out. And if I go all the way in the maximum saturation value, I'm getting the most color I can out of it. Okay? And what's nice about this is if you have an image and you're looking for a particular color, if it looks white, you can't tell what color it is in an RGB value. Okay? Especially not in grayscale. Okay? But this allows you, no matter how washed out it is, you can still get a color value out of it. Okay, it's easier to get that. Then the value is basically how bright is the color. The top there, you see that's the brightest, truest color, and on the bottom it's basically black. Okay, so that can be useful if you're trying to detect colors. And if you want to convert in Scikit image, I've already shown you how to convert between RGB and gray in OpenCV. In Scikit image.color you can do that. You can also convert RGB to HSV. Okay, there's another one that's called YUV, and that's sort of a legacy of old television signals. And what's nice about YUV is that one of the layers is the grayscale value. So if you want to convert grayscale, you just throw away 2 of the layers and you use that. So 2 of them tell you what the color is, and the other will tell you what the grayscale is. It was really useful when you were going between color and black and white TVs. Back in I remember, when I was a little kid, we only had black and white TVs. So in that transition between black and white and color, that was a really great color space, because you could send all the stuff and it was a black and white TV. You just peel off the top one and ignore the bottom ones. So all sorts of color spaces. Everyone has their own pet about which one is the best. My experience is HSV works really well when you're looking for particular colors. So I did my color histogram in the HSV color space. You probably would get similar results in RGB, but it's been amazing. I've done some machine learning things and just simply changed the color space and got dramatically different results. So it does actually matter sometimes what color space you use. Okay. All right. That's what we got for today. Next time we'll actually talk about machine learning instead of